in the 1940s. Already go up, this kind of study already went up when they built up the first computer. They already think about random noise very long time ago. The second type, or the second area, is mathematical physics and probability, and we have quite a few talks about this at this conference. And the main purpose here is to study the distributions of eigenvalues, both in global and local statistics sense. It goes back to the study of Wigners in 1950s. And the combinatorial aspect, which is this talk, it is harder to define, but I will give you a lot of examples to, so that you can have a feeling that what is a combinatorial problem is concerning random matrices. The thing I really enjoy when studying this topic is that we have seen a lot of interaction between this theory and many other areas of mathematics. So, Terry is going to give a tutorial talk about this. And also, there is a book come out by AMS when we have several surveys. So about a year and a half ago, I helped the AMS to organize a mini course to cover all this area, and we managed to force a few experts to write introductions to this area in the sense that normal people can understand. And those surveys now appear from in the proceeding by the AMS, just in case that you want to learn the outline of these areas and the interactions between them. Okay. And another thing that I really like about working, to sort of talk into these combinatorial questions, because these questions are very simple to state. You don't need any prior knowledge about random matrices. And on the other hand, they are very good model problem to build up a new idea. And actually, it's very rewarding in the sense that we come to a few new concepts that appear to be very useful in solving other problems from which was open in other areas of mathematics. So that's what another things that I want to emphasize. Okay, so here's the few problems that I like to discuss, just to give the flavor about the field or a topic. And there are many more in the ICM papers that I written. So the first one is my favorite. This is very simple problem. You have I call it, or we call it, the singularity problem. Namely, that you have a random matrix. So think of this plus minus one random sign matrix. How often is it singular? Okay, so it's a discrete distribution, and this probability is not zero. We want to bound it. And you can ask the same thing. If the matrix is not singular, then the determinant will be non-zero. So if it is not zero, then what would be the typical value of it? How is it distributed? Or you can ask the same thing for the permanent, which is another combinatorial quantity which has been studied a lot in combinatorics. Or you can ask questions about the eigenvectors as well, not only the eigenvalues. So all these are sort of related to the eigenvalues. But you can look at an eigenvector of a random matrix and see that, okay, ask the question that how does a typical eigenvector look like? So we all know that when people study random algorithms or spectral algorithm on graphs know that eigenvectors play quite an important role there. It's important to know this kind of the answer to this kind of questions. Okay, so let me start with the most famous problem in this area, the singularity problem for the non-symmetric matrices. Yeah, so again, the model is here. We have let's stay with the plus minus one, but you can think of any other discrete distribution as well. So we have a plus minus one matrix. We have n squared random bit in the matrix, and call it Mn. Then what is the chance that it is singular, which I denote by Pn? There is a well-known conjecture, which is very old and notoriously hard, saying that this is about half to the n. And the lower bound is obvious. The matrix would be singular if you have two equal rows of column. So if you fix the first row, the chance that the second row equal to it is apparently half to the n. So you would have this half to the n here, and you can choose any two columns and rows you want, so you get the extra n squared. So the sense of it is that the singularity came from small obstruction, so it's the obstruction involve only two rows. The dependency of the matrix involve only two rows. You can ask that what happens if we consider 3 rows and 4 rows and so on, and there is a more precise form of the lower bound computed by Arashia et al. A few years ago that give you the answer for the lower bound, a more precise answer for the lower bound. Yeah, but our upper bound is still not quite matched, so that's the story I want to tell now. The first upper bound was proved by Kumlos in '67, which is simply just showing that this probability going to 0 as n go to infinity. And that was already hard. The original proof of Kumlos is quite complicated and very nice to read actually if you want to look back at these papers. Let me give you now a new proof which is simpler and which also gives rise to some new intuition and concept that become useful later on. So here's the short proof of Kumlos theorem. Okay, so yeah, so Pm, let me remind you, is a probability that the matrix is singular. And let me go x1, x2, up to xn, the rows of the matrix. And we sort of expose these rows one at a time. Now, if the matrix is singular, then at some point I, the row number I plus 1 should be part of the subspace spanned by the rows x1 up to xi. Right? So that is a definition of linear dependency, which have to happen sooner or later. Okay, so now we want to bound the right hand side here and look at some step number D. Well, if we want to bound this probability, we want to know first that how many plus minus 1 vectors belong to the span. And there's a simple fact that if you have a subspace of dimension D, and it doesn't contain more than 2 to the D plus minus 1 vector. Because by definition, any vector in the dimension D is determined by the set of D coordinates, and you have only 2 to the D choices for these coordinates. Okay, so the span here will contain no more than 2 to the I plus minus 1 vector. So you put this into the sum, what you would get is this sum, right? Which is a geometric sum, very easy to estimate, and this gives you this precise answer. Now, this at the first look is pretty bad because we want to prove the whole thing go to 0, and here it go to 1, and this go to 1 very fast as well. But now you look at this sum with the geometric series, so actually all the contribution comes at the end. So the idea is that it's enough that to break the sum at some point, say we look at the last, say, log n terms, and if we can prove that the contributions coming from the last log n term is going to 0, then we are actually done, right? So what I'm going to do now is actually say the last contribution is something like 1 over log n to the 1/3, say. If we have this, and then we play it against log n, okay, so the last distribution, the last contribution turned out to be the biggest one as well, so we can use it to bound all the other terms. So if we have this, then we will have log n divided by log n to the 1/3, which go to 0, and the rest of the sum also go to 0, and we are done. Okay? Yeah, and so this requires small observation that with high probability, if you look at the span of the first n-1 vector, and look at the normal vector of that. So if this guy forms a hyperplane, say, and the normal vector of that is, we can prove that it has at least less than non-zero coordinates with high probability. And that probability is very close to 1. You don't have to worry about the error term here. And then we use the classical theorem or lemma of Littlewood, Oxford, and others back from the 40s, which says the following. If you have L non-zero numbers and look at this sum, random sum, A1 like C1 plus AL up to CL, when Ci, as I mentioned, is just a plus minus 1 random variable, then this probability is bounded from above by 1 over square root L. So this was proved in a little weaker form by Littlewood and Oxford as a particular for some particular purposes, which I cannot discuss here, and it was improved by others in this optimal form. Now, if we have this and we try to use this in our setting, then we look at the event that Xn belongs to this subspace or hyperplane. It is the same as the event that Xn times the normal vector, the dot product of these two guys equals 0. Yeah, but the dot product can be written in this linear form, of course, when the AI are the coordinates of V. So, and we know that the normal vector have many non-zero coordinates, so we can have this bound. Here, the vector is L to the minus half, and it is like log n to the minus half is less than log n to the minus 1/3, and we are done. Okay, so that is the short proof. Now, of course, the little O of 1 is just the little O of 1 by Kumlos is just the beginning, and there is a range of further developments. Kumlos himself improved it to 1 to the square root n. It's another nice argument. It's completely different from his original proof, actually. It appeared in the books by Bolovash. More importantly, there's a very important and nice result of Kahn and Kumlos, Singularity 95, bring the first exponential value to the n. So we know that the conjecture value is half to the n, but they can do 1.99 n, 1 minus epsilon to the n. About 10 years ago, Terence Howard, I improved it to about 3/4 to the n. And 3 years later, Bugan and my student Wood improved it a little bit further to 1 over square root 2 to the n. And that is the state of the art now. So let me tell you a little bit about the last result and also the tools behind the proof, which will lead to some new concept. So actually, what we proved with Bugan and Wood is a more general theorem, which says the following, that if you give me a random matrix with some even more general distribution, not necessarily plus minus 1, but any discrete distribution, then there is a way to write a host of trigonometric inequalities using that distribution. And after you write this, then you can read the bound directly from here. So here's an example. If you give me the plus minus 1, I can write actually many inequalities, but 2 of them are like this. And you can check that it's actually, they are obviously true. And the 3/4 bound comes from this one. So I will show you that we have the bound at 3/4 here. And the square root 1/2 comes from here, so you see that half on the right hand side, but unfortunately we have to square this cosine, so we have to take the square root of this, and that give you the other bound. Well, it sounds a little bit like science fiction now, but the truth is that it's indeed about from these simple things. And in some instances, for some certain distributions, we can even have a sharp bound. For instance, there's the model for lazy code flip matrix. So you can see this model in Van Green talk as well. So we don't flip the code immediately, but we just take it to be 0 first with, say, probability half. And after that, I flip the code and take plus minus 1 with probability a quarter. Now in this matrix, the singular probability is also lower bounded by half to the n, because the probability, let's say the first row is O0, is already half to the n. Right? And we can prove the sharp upper bound for this using one of these relations. So just come out from there. Okay, so yeah, so what is the tools behind this? There are two main tools that we use. The first is the dominating principle that appeared already first established by Holland in the 1970s and used in the KKSD paper. And the second one, which I like to spend a little bit of time on, is the inverse Littlewood-Oxford theory. Okay, so what is the Littlewood-Oxford or the inverse Littlewood-Oxford? Before talking about the inverse, let me spend a few minutes on the forward result. Okay, so we can go back to the result, original one by Littlewood-Oxford and others. So what is the extent of this? We have a bunch of numbers. We consider this linear sum, this linear form, say the product with random bits here, and say that the probability that equals 0 is bounded by something. And this is sharp. It's easy to show that is the order L to the minus 1/2 is sharp. Well, that was not the end of the story. So thanks to the beautiful proof by others, this result became very popular in combinatorics, and it gave rise to a host of other studies. For instance, back in the 1940s, Erdős and Moshe asked the question that, okay, what if I put more assumptions on the AI? Can you have a better bound? And they show basically that, for instance, if I say, if we assume that the AIs are different, then actually the bound will jump to L to the minus 3/2 instead of minus 1/2. And it was conjectured by Erdős and Moshe and proved by Sarkozy and Symmetric. Erdős and Moshe themselves put a slightly weaker theorem. Stanley gave a characterization of the extremal set in this. Actually, it was his first talk at ICM in 83. A little bit hard to find because he gave the talk in the algebra section, not the combinatorial section. But it was because his proof, well, it turned out to use very hard algebraic tools. So what he can show is that if you assume that the AI are different numbers and want to optimize its probability to make it as big as possible, then the best way is to take the least n numbers with the least absolute value. Right? So you look at this guy and say that if you take the sum of the square of this guy, you can actually this set minimize the sum of the square of n different integers. That was the Stanley result back from the 80s. And then there are a lot of extension and sharpening of this result by many researchers, well, particularly from the Hungarian school of combinatorics. Okay, so the new concept that we introduced is the following, which is very close to the concept that Ben Green talked about in his talk this morning, that namely, if the probability is large, then the set can be characterized. So what does this probability is large means? Well, if you look at this probability to be 0, and you think about the CI as plus minus one random bit, and say if you assume a little bit furthermore that the sum of all the AI are zero, then actually we are talking about subset sum of the AI, right? So what the probability here is just counting the number of subset sum of the AI hitting zero. And if the probability is large, that means that many subsets have the same sum. If you remember the bandwidth talking this morning, he don't talk about subset, but he talk about many pairs having the same sum. But that is more like, well, in spirit, very close phenomenon, which we in additive combinatorics called this is a phenomenon established first by Feynman. That in such a cases we expect to have a rigidity or a structural theorem, and we can characterize these sets. There's a lot of papers developing this concept. I think Ruth Escher and Bershainim talk about this in their talk in the last ICM as well. And let me show you one simple result that came out. For instance, that we assume that the probability is larger than some fixed negative power of n, then the whole set, or more or less the whole set, should belong to some arithmetic progression of some other power of n. And you can check that this statement actually works both ways, namely that you assume that AI belongs to such an arithmetic progression, you have this bound. And what we prove is that the inverse direction is also true. That's how we call it the inverse Wilhelm theorems. Now you can imagine that how we can improve the result from this proof. So very simply, you go back here and look at this bound and say that, okay, now I want a much weaker bound, which is not L to the minus 1/2 anymore. I assume that this is something. Now, if this probability is small, and I already done because that is sort of my goal. If the probability is large, then actually I come back and say that, okay, now the AI has some structure in them, which on the other hand would be impossible as well because the AI is the normal vector come from the normal vector of a hyperplane. And the hyperplane itself is random, so actually the chance that the AI have some structure in them is also very small. And by playing this game and balancing between the two small probabilities, you can greatly improve this bound, and that leads to all this development that I show here. It was used in the 3/4 and 1/√half bound. Yeah, so I mentioned that the combinatorial problem is nice to develop this concept, and the concept actually was very rewarding because it's found an application in a very classical problem in probability. Namely, we can use it to establish the so-called circular law conjecture concerning the eigenvalues of Mn. So as I said in the beginning, in the big picture of the field of matrix theory, that one of the main, in the probability and mathematical physics part of it, one of the main objects is determining the limiting laws of the spectrum. And here the conjecture is the following. Mn is a non-symmetric matrix, so the eigenvalues are more or less complex. And the conjecture say that after a proper normalization, the limiting distribution of this complex number is uniform on the unit circle. And that is the conjecture. It has been known since the 60s, but only later on, I think the proof is finished in 07, and we have a survey in 09 that covered it. So that's one of the examples that I want to mention, that combinatorial tools now can be applied in classical probabilistic problems. So now let me jump to the case. The next one, actually before that, there's some other things I also want to mention, that one can also reprove the study result in a little bit different way. In a little bit different sense, it's asymptotic result, but it is stable, namely that if you have a set V that give you the probability close to the optimal set, then the set V itself also have to be close to the optimal set. So that is something very much similar in spirit to rigidity theorem in extremal combinatorics, like talking about graphs or something like that. So here you can do the same thing as well, thanks to this structural theorem, the inverse theorems. Okay, so now let me go to the next thing, which is the symmetric case, just again to give you some flavor of the study. Okay, the problem is the same, just the only thing I change is instead of considering non-symmetric matrices, I consider symmetric one, and I ask the same questions. Right? Actually, it was surprising to me when I gave a talk about the non-symmetric matrix, and actually people in the audience, I think Yin Kalai or Natilino, asked me what happened if you have a symmetric matrix. I thought that it should have been solved long ago by Comblos back in the 60s, because it's so natural question. But apparently not, and I think both Nati and Gil mentioned to me that it was actually a conjecture by Benji Weiss, that they didn't know that this go to zero with n goes to infinity. And so we can prove this, actually managed to prove some quantitative result as well. And the main tool here is that you need a quadratic version of the Littlewood Oxford Erdős lemma, which I now introduce. So if you recall, the original Littlewood Oxford, let me go back just to make refresh your memory. The original looked like this. You have a linear form in the term of the random variables, and you want to bound the probability that this is zero. What happens if you replace the linear form by a quadratic form, right? So now you have just a second degree polynomial in the CI. Our proof of the Weiss conjecture based on the fact that the probability of this begins zero, go to zero with n, and later on Costello can prove the optimal bound, which is n to the minus half, similar to the linear case. We don't know any generalization of this, so what happened with the third degree polynomial, what is optimal bound for the third degree, we don't know. It's totally open and would be of interest because I think here there's some higher degree polynomial result, and Raskolov and Viola found some quite a fascinating application of it in complexity theory that would help if you have nice bound on this. But so far, the bound for higher degree polynomial are pretty poor. So let me go to the state of the art of the symmetric case. So if you want to make a conjecture, I think the natural one is, again, conjecture is hard to the end. At least I think so. Maybe there's some obvious counterexample that I missed. But unlike the Comblos problem or Comblos result, the improvement still doesn't reach the exponential stage yet. So Ho and my former student proved the first super polynomial bound, and what he did was to develop an inverse quadratic theorems. the best bound dual to the shiny now is, well, it looks exponential, but not yet actually, because the epsilon here is not 1, it is something like 1 over 10 or something of that order. And it's not because you don't optimize a constant. There's a deep reason why you cannot get close to 1. Yes, so it's totally open to prove an exponential value on this. Okay. So in the rest of the talk, I think I just give you some other open problems which come very naturally in this study. One of them is about the rank of the random graphs. So everything I say for plus minus 1 matrix would be true for, say, 0, 1 matrix as well. So you can talk about adjacency matrix of the random graph. And when you talk about the adjacency matrix of the random graph, then we have a freedom to choose the density P. So a random graph is just graph you draw by picking a pair of vertices and draw an edge between them with probability P. And P can depend on n. P can be something like 1 over square root n. Yeah. So okay, so we have this result for P equal 1/2, just equivalent to the result for the Wise conjecture. And you can easily prove it for all other constants, but about known constant P. Now, people are familiar with the random graph theory would quickly recognize that there's some problem if P is very small, because if P is less than log n over n, then there will be a lot of isolated vertices. And if you look at the adjacency of the matrix, of the graph with many isolated vertices, it will have many 0 rows, right? So isolated vertices have no adjacent neighbor. So in the rows corresponding to these vertices, all you see are 0. And then, of course, the matrix is surely singular. And we can prove that this log n over n is the correct bound. And more, if we go to the range where you can even see isolated vertices, so now of course the matrix is singular, but there's still a question to ask. For instance, you can ask how singular it is, or, well, quantitatively, what is the co-rank of this matrix? And one thing which is satisfying from here is that we can prove that the co-rank all come from small local obstructions. So if you remember the bound 1/2 to the n at the beginning, it comes from the local obstruction that you have 2 rows, they are the same, right? And there is, well, we cannot prove that kind of result anywhere that saying that, okay, here the main reason for singularity is these local small obstructions. It is only instance, I know that when we can prove it. And the local small obstruction is very simple to describe. They are just a small set of number of vertices when the number of neighbors is less than the number of vertices in the set. In the linear algebra term, it means that you have, say, 5 rows. We have only 4 non-zero numbers in it. Then of course these 5 rows are linearly dependent, and it gives you some addition to the co-rank. So we can show that all the co-rank comes from this. And in the even smaller range, the range of the giant component, well, if you don't know what the giant component is, it doesn't matter. In the range when P is the constant over n, people compute the asymptotic of the rank, but not precise. And so, a question to ask here that if you can have the same result characterizing the co-rank. An even more interesting question is that what can you tell about the limiting distribution of the eigenvalues of the giant component? Right. So the giant component is a very well studied object in random graph theory, but in the spectral sense, this question is seem open. For instance, I don't know if the limiting distribution is smooth or it has an atom. That I think is also open. Okay, so so I just give you one or two other questions to have to give you the flavor of the kind of things we can do. And the thing I like about this question is that they are very simple to state, and I am almost certain that in the solution we will find some very new and quite applicable new ideas that will be useful for many other things. So after all, that's the purpose of that we prove theorems, not for the theorems themselves, but to have some new insight into things that seem complicated. So here's one of them. Instead of the average linear graph, let me talk of another models of random graphs. So you can talk about random regular graphs. So let's say fix this degree to be 4, and you consider O graph which have regular with degree 4 on n vertices. You choose one of them uniformly randomly. There may be a million of them, just choose one. And the conjecture is that this uniformly chosen random graph will be non-singular for all value of d. And it is not known, and it is not known for any value of d. Well, the case d equal to 2, the conjecture is not true. It's easy to disprove it. Recently, Nick Cook proved a directed case, which is already quite hard. And in this matrix, by directed, he means that he generates a matrix when the row and column sum up to D, and it's 0, 1 matrix, and all the row and columns have the right degree, but it is not a symmetric matrix, so we don't know. Yeah, so here's the final conjecture that I want to mention as well. If you take the same matrix and look at the extreme eigenvalues of this, so the first one is just a degree, which is d, but well, of course we know the story. What really matters is the second eigenvalues, and we conjecture that should be of order square root d, which agree with the Erdős-Rényi case. And Friedman and Kahn and Symmetric proved it for constant d. In fact, Friedman, in a very sophisticated paper, derived the asymptotic of this is roughly 2 times square root d minus 1. The Kahn-Symmetric result extend to d less than square root n. And you can see this some paper of Alan Fries. So it was sort of a null phenomenon. But beyond this, we don't know, for instance, in the base case, when d is n-half, which corresponds to Erdős-Rényi graph with probability half, which is a very basic case. The best bound I know have an extra loop in it, and I don't know how to remove it. So let me end the talk here. There's many other problems which in the ICM paper that you can look at. And thank you very much.
Thank you very much. I think we have a time for question. Yes, please. Ask.
You gave those couple of trigonometric inequalities, which you said gave the bounds of 3/4.
Yes.
1/√2. Can you say anything about how those are used?
It's a long story, so yeah. So we have a procedure that you give me the distribution and come up with a family of inequalities like that, and among them I can choose the best one that each of them give rise to a bound, and I can choose the best one to give me the best bound. And the bound is not always sharp. It's sometimes sharp, sometimes they are not. But the statement itself is slightly technical. I'm very happy to give you the paper. Yeah.
Winter?
Have you looked at numerical evidence for these conjectures, like for symmetric matrices, the 1/2 or for the random regular?
Oh, the random regular, people look at this quite a bit and they have that conclusion. For the 1/2 to the n, actually I didn't test because somehow if n is like 200, it's already hard to see any instance which is singular at all. So it's hard to test.
Brandon?
If you take this plus minus 1 matrix, that one that you start with, and then
Yes.
you condition it on the rows and columns all assigned to 0.
Yes.
Of course it's singular, but is the multiplicity of 0 almost certainly 1?
Yes, yes, that's correct. Yes.
Other questions? If not, let us thank Anvo again.